minus x. Minus 1. Looks much nicer.
Can you explain that?
Oh, what is my definition? Sorry. I'm sorry, sir.
Can you explain that stuff?
You mean from here to here?
Yeah.
Here's what I really do. I convince myself that this right here is a common denominator for these three fractions. So I multiply top and bottom of the first one by whatever I have to get that 2x root x downstairs. And with the second fraction, I dove in and said, well, if I multiply top and bottom by green x, that would build us up into a denominator that is the LCM. And I committed that upstairs as well. Sounds reasonable. Actually, you're going to be right. It's just that I haven't talked about differentiating the composition of two functions, so just using the rules I have today, how should I differentiate? I think I have to expand.
Yeah.
With my math D skills, expanding hard BC. No calculus. Isn't that just simply an x cubed of think French? Pascal. 3 x squared. Oh, shoot, now we can differentiate. F prime of x clearly is
2x squared plus 6x plus 3.
If you wanted to serve whoever you differentiate first, if you really wanted to, you can pull out 3 on it. If you really wanted to, you can rewrite that binomial. That trinomial is this binomial squared. Getting exactly what you said. Just to show you that you really are right.
Okay, so you can do it either way?
No, I'm saying you can't do it his way yet at all officially because I haven't given you something called a chain rule. Whatever that is.
Does it always work like that?
Yeah. Well, no, this is too much work. I'll give you an even shorter cut.
Wait, no, can't you just do it anyway? I mean, because first you just do that, and then next you just use t times f of x.
I would hate to use any mathematical process without proving it first.
Well, but you've already proved those two.
Oh, but I've proven nothing about composition of functions, which is a chain rule. Whatever that does. And so I don't have any rules in the field over here that allows me to differentiate the composition of this linear function with the cubic function.
I don't understand. So first you're using the what's it called?
The power rule?
The power rule. And then next you can just use the derivative of c times f of x equals c derivative of f of x.
Well, no, because there is no derivative of a constant. There is no constant in here. Once you bring the 3 down, you've already differentiated.
Oh, I see.
So I think it's a much more complex process. Now, I admit in this example, what's being cubed is so well behaved, it turns out to be very nice in the end. It's just if I mess this up like a 2x plus 3, then I think there's going to be some problems. And there will be, trust me.
So, do we have to go through those steps to get the f prime of x for what you gave us there? Or
Tonight we do, because I haven't talked about differentiating the composition of functions.
Oh, okay, because it just looked like what we were doing with the power.
I know. But it's not because what's being cubed is not a simple x. What's being cubed is more complex than x, therefore, that requires some more machinery. We'll get in the next class.
But only for today.
Yeah, only
Later
for
on.
tonight. Oh, you know what? I can add to my list. Another check mark. To differentiate with respect to x. X to the n. So you guys, let's try to check this out. Let's try to develop this. Are you ready? Complete silence in this room. Are you ready?
Yes.
No, we've already done it. We know how to differentiate differentiated power expression where x is a variable downstairs and n is a constant upstairs. So let's do something different. Let's do something like this. Let's differentiate an exponential expression where now the base is a constant and the variable, the independent variable, is up in the exponential position. To do this, I'm not going to use logarithmic differentiation yet, but what I will do is this. I'll go back to my definition. And I think f prime of x, by definition, is a limit. As h goes to 0, we cannot possibly have that.
Could you just turn the screensaver on?
Yeah, I can. It's just that since so many other professors come in here, we don't want to change the setting. We want all the rooms to be exactly the same. And it helps repair the computers when they fail.
As soon as I restart, it'll go back.
Now, well, actually, you're right. I can do it temporarily. Do I get this? Or shall I say this? That wasn't me, was it? Oh, good. Is that this? Sorry, can I pick a specific function out? How about one whose base is 2? My apologies. Or how about this?
Yep.
Or how about this? Pulling out a common factor 2 to the x has nothing to do with h. I can pull it all the way outside the limit.
I'm sorry, stupid question. Can you remind me again about the addition and the multiplication part of it?
Yeah, you know what I really did from here to here? I was doing something this simplistic. I said a to the m times a to the n could be interpreted as a to the sum of those two powers. I just went backwards.
Okay.
I said when I have addition in the exponential position, it converts to multiplication in base position, assuming the bases are the same. Yes?
Oh, never mind.
Do you guys agree? That limit really is in an indeterminate form. Plug 0 for h, don't you get 0 divided by 0? Okay. If you do, I have no hand waving to do. I can't set up in front of the entire class and show you how to analytically evaluate the limit. I'm going to do something different. I'm going to use my technology to suggest perhaps what this limit really is. So if I pull out my nifty, where are you, calculator. And I type in my y equals 2 to the x minus 1. All divided by my x. Okay, I'm using x instead of h's. Same thing, isn't it? And only because I can tell someone's been on this computer doing stats, it might cause a problem. Can I take a quick break and go into stat clock and turn it off? Just so I have to, oh, it is off. My apologies. So I think then, if I set up a table of values to find out what this thing does as h goes to 0, I'll start an h value of how about 0? An increment. By 0.01 looks good to me. And let's see what my table suggests. Going into my table menu list. Notice how x gets smaller and smaller, getting closer and closer to 0. The corresponding y values seem to be getting close to something like 0.69, whatever that is. Actually, let me zoom in really far. Let me go into my table set. I'm going to increment my table values by not 0.01, but 0.0001. And now let's check out what happens. To this algebraic expression as x goes to 0, it's getting closer and closer to 0.69317. Actually, if I get out of here and I compute the natural log of 2, it's that value. As a matter of fact, I think this ends up evaluating to nothing more than a constant, which is the natural log of the base of my exponential expression. which means this is now how I'm gonna differentiate the exponential function basis 2. Let me repeat that. I think of my basis A, I'll differentiate by having nothing more than this constant, the natural log of the base is just a constant, times a to the x power. Which means, if I were to differentiate with respect to x, the natural exponential function, I'm going to get e to the x power times a constant coefficient, which is a natural log of a. And what's the natural log of a? What's the natural log of e? I missed one. 1. Nobody jumped. Look at what this says. This says, for the graph of y equals e to the x, the slope of the tangent line is nothing more than the y value. That means, graphically speaking, this function is truly, truly unique in mathematics. No other non-trivial function behaves like this, where I've got my darn curve, whatever it looks like, you grab an arbitrary point on the curve, call it a comma b. Then the slope of the tangent line, the slope of that line is going to be b, the y coordinate. What? Yes, that is really impressive. That's very impressive. And we've just tried that. And that's true no matter where that point is. Nabil. Oh,
Does that really count as a proof?
You're right, because I evaluated the limit with number crunching. That's true. I agree with
So
that.
it's not technically the proof, it's like...
Yeah, I can't really technically prove this to you until I start talking about something called implicit differentiation, whatever that is. But I've got strong suggestions.
Okay.
So e to the x is its own derivative. It's the only non-trivial function that's its own derivative. The trivial function that's its own derivative is the y equals x, y equals
0?
yes. Oh, you guys, my examples, what number am I on? 4? Well, that really wasn't an example, was it? That was playtime. All right, you guys, let's see how awake you are. Very nice. Very nice.
Plus 2.
The natural log of the base is a constant coefficient times that exponential expression right back, plus very nice. I heard that. Very good.
I'm so confused.
Are you really? Which one?
The e to the pi became pi minus 1.
You mean this one right here?
Yeah.
Well, yes or no. Is that a variable raised to a constant?
Yes.
Then I use a power rule. I bring the pi down, the n down.
No,
I reduce the n by 1. Now, is this exponential or a power? Which one? I think it's just a constant. It's just a constant for any constant is 0.
Oh, I thought that represented that one.
No, I'm going in order.
Oh, okay.
I'm just curious about the last one.
Well, do you agree there are no x's? So this is sort of like a 7. In a differentiated constant, you just get 0 right back. Maybe?
For the third and the fourth terms, so, okay, so it's the derivative of 2x, you get natural log of the base times 2x. And then for that one, oh, I was looking one ahead. Okay, never mind.
Because that still is, I think, an exponential expression.
Yeah, okay.
The base
okay,
just
got
happens to
it.
be the
Okay.
number pi.
I thought that was for x to the pi, and I was really confused.
Gotcha.
Okay, gotcha.
Ooh.
It looks like a 20.
20 for you?
You guys, are you ready
Video
for the
quality
big
better than
guns?
mine.
1080p.
No. You're not. Ah, shoot, you've never seen this before. I guess I better, go back to my definition. Now going back to math D, I think I can expand a tad bit. That's the limit as h does this thing of f of x plus h times g of x plus h minus f of x times g of x all over h. And you guys, I know when it's convenient, I tend to multiply by forms of 1 to make things legal. But instead of multiply by 1, how about if I just add something? Add a funky looking form of 0. Here's a funky form of 0 I'm going to choose. How about a minus f of x plus h times g of x plus f of x plus h times g of x? Perfectly legal. It's just a funky looking blue form of 0. It's just that if I split this big fraction up right here, take a mathematical axe right there, I think what that gives me is a limit as h goes to 0. Well, you guys take a peek at these two terms upstairs. They have a common factor of this. Let me pull it out. Now, the limit of a sum is the sum of two limits, so let me split up the two limits, plus the limit as h goes to 0 of, actually, if you take a peek at these two terms, you guys, something else happens. I got a common factor g of x, I can pull it out. And here's what's left over. Oh, I heard some grunts. You see it. But that gives me, let's see, doesn't that give me the limit of a product? That's the product of two limits. And so I think I'm left with a limit as h goes to 0, the first factor, times the limit as h goes to 0 of the second factor, plus oh, you guys, check this out here too. I got the limit of product. That's a product of two limits. So I guess I've got the limit as h goes to 0 of my g of x, times the limit as h does its thing of this difference quotient. Well, let's take a break, and let's merely evaluate where appropriate. As h goes to 0, what's another name for the first factor? Do you recognize the second factor? Plus times. That's so important, I'll give it a name. I call this my product rule. To differentiate the product of two functions, I get the first times the derivative of the second plus the second times the derivative of the first. And by the way, with the string of multiplication and addition, order is not important. Both addition and multiplication commute in the real number system. So you don't have to worry about order here. But at least it gives you and I a technique for differentiating the product of two functions.
It's not a lot of space.
Oh, I think it'll be more than enough. Is it just a one-liner? It's the natural log of 3 times 3x times
X. Oh.
next to that plus 3x
Square
squared times, times,
3x squared?
times
Oh, no.
3 to the x. Oh, it's time to pull out your mathematical broom, clean up. The blood's rushing out of my arm, it's going numb.
I don't get it.
Oh, did you get up to this point?
No.
Okay, don't listen to me. I think the product rule says this. I got the first as is, times the derivative with respect to x of the second. Plus the product rule says the second as is don't touch, times the derivative with respect to x of the first.
It's the same thing.
I know. Well, and if I flip, I don't even notice that because it doesn't really matter. But I think this is nothing more than 3 to the x times, oh shoot, wait, you gotta differentiate here, power rule. Plus x cubed times, oh hold it, yet again, I got a differentiation process, but
Yeah.
I'm differentiating an exponential expression.
Okay.
Because we always carry those mathematical rooms in our back pocket. You guys just don't want to play anymore. Well, what do they have in common?
3x.
Yeah, they have a 3x in common. What else? X to the second. And let's just talk about what the heck really reigns standing on either side of the addition operation. Would that give me is that a 3 plus, I don't know, is that a natural log of 3 times x?